Today we're going to be talking about PFAS compounds. Me and Mr. Dev are experts in this field of science.
We will cover where PFAS can be found, how electronegativity applies, different types of properties, and why PFAS should be a concern to humans.
First off, let's explain what PFAS even is. PFAS stands for polyfluoroalkyl substances. These substances are found in kitchen cookware such as non-stick pots and pans. These substances are also found in microwavable popcorn bags, pizza boxes, dental floss, firefighting foam, certain cosmetics, paints, varnishes, and sealants. Basically, you get the picture. Anyway, I'm going to bring it over to Mr. Dev, who is going to explain the science of electronegativity.
Whether a bond is nonpolar or polar covalent, it is determined by a property of the bonding atoms called electronegativity. Electronegativity is a measure of the tendency of an atom to attract electrons toward itself. It determines how shared electrons are distributed between two atoms in a bond. There are more strongly an atom's attract to the elements in its bonds, the larger the electronegativity. The Greek letter delta. No, not that delta. This delta. This letter symbolizes the change or difference. It is utilized in chemical equations as a variable that indicates change that happened in a chemical equation. Thus, the plus and minus indicates the partial changes in atoms within a molecule. If there's a plus, it indicates an atom is less electronegativity, while the minus indicates it is more electronegative. Bonds. We all have them. Family bonds, friendship bonds, and chemical bonds. There are three types of bonds in PFAS, C, F, and I. The electronegativity of these bonds are measured using the Pauling scale. The electronegativity of C, F, and I are 2.55, 3.98, and 2.66 respectively. The differences between a CF and a CI bond are that the CF bonds are exceptionally strong, short, and highly polar due to the fluorine's high electronegativity of 4. In contrast, CI bonds are weaker, longer, and less polar. CF bonds offer high stability and resist oxidation, while CI bonds are more reactive. A bond dipole measures the polarity of the chemical bond, representing the uneven distribution of electron density between two bonded atoms with different electronegativities. In the context of PFAS, the polarity of a CF bond is much higher than a CI bond due to extreme electronegative differences. Although the polarity is much higher, this occurs at a low dipole moment. Back to you, Grif.
Thank you, Mr. Dev, for your insight. Now we will discuss some key terms that are important in understanding the relationship between bonds. The first key term that we're going to go over is atomic radius. Now, atomic radius is the measurement from an atom's nucleus to its outer electron shell. The atomic radius tells us how large an atom is. Additionally, on the periodic table, atomic radius will increase as you go down a group, and it will decrease as you go across a period. The second key term that we're going to look at is bond length. Now, bond length is the distance between the centers of two atoms that have been covalently bonded together. Similar to atomic radius, bond length also increases down a group and decreases across a period on the periodic table. The third thing we're going to talk about is correlating bond strength and bond length. Bond strength and bond length are inversely related to one another. When a bond is shorter, the strength of the bond is stronger. However, when a bond is longer, the strength of the bond is weaker.
Earlier, we covered the types of bonds associated with PFAS. Now, we will cover bonds at enthalpy. Bond enthalpy is the measure of energy required to break one mole of a specific covalent bond between two atoms in the gaseous state, measured in kilojoules per mole. In the context of PFAS, the bond enthalpy requires very high energy to break CF bonds of roughly 485 kilojoules per mole. CI bonds break at significantly weaker rates of roughly 200 to 250 kilojoules per mole.
Earlier, we explained where PFAS could be found, but in this section, we will identify the effects of PFAS on humans. Believe it or not, human interaction with PFAS can have negative effects and consequences. Some health concerns caused by PFAS are increased risk for certain types of cancers, specifically prostate and kidney cancers, It can also cause increased cholesterol levels, and it can also cause a compromised immune system. Those are just few of many negative effects that PFAS can have on humans. Additionally, humans can be tested for PFAS through blood tests. These blood tests are then analyzed in a lab to determine whether or not a person actually has PFAS in their bloodstream.
Despite the things PFAS is used for and its scientific properties, PFAS isn't the most pleasant thing in the world. There is a dark side to these forever chemicals. In fact, in this year's Winter Olympics, the International Ski and Snowboard Federation marked the first game to ban the use of PFAS in ski and snowboard wax. The reason they enacted this ban was because PFAS reduced friction against snowboard between the board and the snow. That created an essentially clear slate for the athletes to ride down, creating an unfair advantage against other athletes. This advantage was so unfair that it could shave off a fraction of a second to a few seconds of a time during a run.
Finally, we will talk about the United States and PFAS. Government organizations in the United States, such as the EPA or the Environmental Protection Agency, have limited the amount of PFAS in certain items. However, most legislation is done on a state level, not a federal one. Many states have banned the use of PFAS in a variety of products. Connecticut and Massachusetts banned the use of PFAS in firefighting equipment in 2024, while several other states adopted similar legislation in 2025, such as New York, New Mexico, California, Illinois, Oregon, and Rhode Island. States have also prohibited the use of PFAS in dental floss, clothing, and children's toys. These states include California, New Mexico, New Hampshire, Minnesota, Vermont, and Colorado. Thanks for listening to our presentation today. Catch you on the flip side.